All right, as you guys remember from yesterday, we did a review of the collision avoidance plotting terminology. I gave you a sheet that had all the different terms on it, and you reviewed those last night. We also went over the distance equals speed times time triangle, or the methodology in which we figure out speed, distance, and time. And we practiced that. And we also talked about the 10th rule, okay, because that's going to be involved in our process today as we go along and do the collision avoidance triangle to figure out what ship is a threat to us on the radar. All right. So I went ahead and gave you a quick reference sheet on what we're going to do today. We're going to break this up into 3 parts. And we're going to do part 1 this morning, and then I'm going to have you practice this on paper on the plotting sheet. We also went over the radar transfer plotting sheet, and we went ahead and looked at the sheet, see how it's laid out. This was designed to help the mariner do paper plots. And so it's broken up with the range scales on one side. We also have 4 corners, boxes of information on the plotting sheet where we can keep track of our CPA distance, bearing, and time, and we can write down the plotting information as we take plots, okay? So that is there for our use, and we'll be using these full-scale radar transfer plotting sheet because that's what you'd be using in the real world. So we gave those to you. So we went over that this morning, and that's set there. All right. Let's go ahead and start a plot. And first of all, we've got to have our own ship data. So I wrote that up here on the board. We're at 000 degrees true at 20 knots. So our story is that we just came around Cape Hatteras and we're northbound heading for New York. And it's a beautiful sunny day out. And we want to practice our plotting because we haven't done it, maybe in a couple of weeks. So we pull out our radar transfer plotting sheet, and we're standing watch, doing our due diligence, and we have our radar is set on 12 nautical miles. Now when we do this, we're going to be, for consistency's sake, and so we can learn it the best way possible, is we're going to do everything in a 12 nautical mile scale, okay? We're also going to do everything in a north-up orientation, or stabilized display, as we've been talking about the last couple of days. We're also going to do everything in a 6-minute plot. And we discussed that at length yesterday. We broke everything out and looked at the mathematics behind the 6-minute plot and what we call the 10th rule. And we spoke about that for the 10th rule. So everything is going to be in a 6-minute plot. And that'll help us learn this as quickly as possible and consistently until we get it down, all right? So we're going to set up our radar transfer plotting sheet as we discussed. So I'm going to go ahead and put my heading flasher on my plotting sheet. I like to use a dashed line. It just makes it different from the other lines that I may put on the plotting sheet. And I'm going to go ahead and put a profile of a vessel in here. Helps me have a graphic orientation of which way my vessel is heading. So there it is. We're underway, we're moving ahead, and lo and behold, a target ship comes into the radar. And so we go ahead and take that target ship and we note the time. I'm just going to say that it's 1400 hours, and that target ship has a range and a bearing at 1400 hours, and that range is going to be 11.5 nautical miles, and the bearing was at 045 degrees true. Okay, so that was the target ship, range and bearing. So once you have that information, we're going to go ahead and take that and plot that position on our radar transfer plotting sheet. So we're going to go ahead and get out your triangles or your roller plot or your parallel rules, whatever you like to use. And we're going to go ahead and plot that on our radar transfer plotting sheet. So we're going to find 045. Now understand that I'm doing this up here on the board and it's not to scale. It's rough. I'm going to count on you guys to do it on the radar transfer plotting sheet along with me. and give me the exact information that you're getting. So I'm going to go out at 0.45 and I'm going to make a little mark on a straight edge. Now, because I'm at the 12 nautical mile scale and the range is 11.5, I can make a little straight line here right out at the edge of my plotting sheet. Okay? Now I'm going to take my compass and I'm going to go to my 12 nautical mile scale on the radar transfer plotting sheet, and I'm going to go to 11.5 nautical miles, and I'm going to go ahead and go out to 11.5 miles and make a arc or a mark at the 11.5 nautical mile scale. Now the first thing we have to do, just like I talked about yesterday, is we want to make sure we have to label everything. And label every single point or line you draw on the plotting sheet. It keeps you organized. All right? If you just start drawing a bunch of lines, especially when we start doing 3 targets at once, you're going to get confused. So we're going to go ahead and label that. Now we're going to follow our labeling we wrote up here on the board. So this is, the first label is R. And that's because it's the first plot, the first plotted position of the target ship. And that's going to be at 1400 hours. Okay? Now we're going to wait 6 minutes because we're doing a 6-minute plot. We have to wait for 6 minutes. And at 14:06 on our bridge clock or our wristwatch, whatever you happen to be using, we're going to take another range and bearing of that target ship, okay? And that range is going to be 9 nautical miles and the bearing is going to be 043 degrees true. We've just taken a second range and bearing, okay? And it's 9 miles and 043 degrees true. So what do you think we do with that now? We're going to go ahead and plot that position on our plotting sheet, just like we did with the first one. Okay? So we're going to go 043 degrees. And because we have the range rings on there, we can draw a line between 8 and 10 on the range rings. Just draw a line there, okay, at 043. Then we're going to take our compass and we're going to repeat the same procedure. We're going to find 9 nautical miles on our 12-mile range ring. Get 9 miles. And we're going to go ahead and put a mark out here at 9 miles. Okay. Once we have that second mark, what are we going to label it? M. That's going to be M. If we follow our labeling, M is the second plotted position of the target ship, and that's going to be at 14:06. Okay? So now that we have 2 plots that are 6 minutes apart, we can now figure out the most important information we need on this target. And that's what I've written over here. We're going to find out the closest point of approach, or what we call CPA distance. Then we're going to find the CPA bearing. In other words, what's the bearing of that target ship as it goes by our ship? And then we're going to calculate the CPA time. We need to know when the possibility is going to be of the closest point of approach. This helps us decide how much time we have to execute a maneuver, if need be. So CPA, distance, bearing, and time. So how do we do that? Well, the first thing we have to establish is the next labeling, okay, drop my ruler, is the relative motion line. Now we find that by taking our straight edge, we draw a line represented starting at R through M, and we're going to take that line down past our ship in the middle of the radar transfer plotting sheet. And we're going to label that line RML. Stands for relative motion line. Now, a lot of people ask me, well, why did they pick R and M? What does that mean? Well, it stands for relative motion, okay? Relative motion line. This line represents the track line that the target ship is traveling down. But that track line is established by our course and speed and his course and speed, okay? And it will stay on that track line as long as those 4 pieces of information stay the same. His course and speed and my course and speed, okay? Now, can we force him to change his course and speed? Typically not, no, right? We're already seeing a development here, according to the rules of the road, that we have a target ship on our starboard side. All right, he's the stand-on vessel, and we are already establishing the fact that we're the give-way vessel. All right, so we're going to have to change our course and speed, and we'll get into that in part 3 of our discussion. Okay, so right now, anytime you get a target on the screen, you want to figure out this information first because you have to establish threat, okay, or potential collision. So we've established RML. Now, in order to find out these 3 pieces of information, you have to take a triangle or something that has a 90-degree edge to it, and you're going to take that and lay that along the relative motion line. And you're going to slide that down until it goes right through where our ship is, okay? And then you're going to take that and draw a line from our ship out to the relative motion line, okay? And it has to be at a 90-degree angle. Where those 2 lines intersect is what we call the CPA. Okay, this is the closest point of approach. CPA is always a line 90 degrees to the relative motion line through our ship in the center of the plotting sheet. Okay? And that's where we establish. So what we're seeing here is that this guy's going to come down the track line and he's going to be the closest he'll ever get to us off the port bow. Okay? Now to find out the first piece of information, CPA distance, it's very simple, guys. All we do is take our compass and we're going to measure the distance from the center of our ship to that CPA point. And then go over to your 12-mile scale, because that's the scale we're using, and you're just going to measure that distance. And I need you to tell me what it is. I know from just doing this a lot, it's about 1.4 nautical miles, okay? It's in that range. You should be within a couple of tenths of that. Your accuracy will build as we do this more and more. I'm not so much looking for a lot of accuracy right now. I'm looking for methodology. And then your accuracy will come as we do more and more of these, okay? All right, so there's our distance of CPA. Now we have to find the bearing. Now, I don't like to insult anybody with this, but I have to just remind everybody of go back to your days of Navigation 101. The definition of a bearing of an object is always from our ship to the other ship. Okay? So in this case, in order to get relative bearing, you're going to take your straight edge, okay? You're going to go from our ship out to the point of CPA. And you're going to read what that bearing is out here, okay? The relative bearing is from us to the object. What I don't want you to do, gentlemen, is give me the reciprocal. The reciprocal would be down here somewhere, and sometimes that happens. People measure it from the CPA back to the ship, and that's not correct. So we always want to go from our ship out to the point of CPA. And what did you guys get for a...
321.
That's in that ballpark. What'd you get? 322. Okay. So the bearing of CPA is 322. Okay. Now the last part is finding the time of CPA. Now, in the older days, we used to do this with on a plotting head, and we used grease pencils. And when we did that, we were able to walk this distance down and find out what the time of CPA is. But we do it a little bit more accurately now, and this is the way I need you to do it. The first thing we have to establish is, in order to figure out the time of CPA, let's look back at our formula. Time is equal to distance divided by speed, isn't it? Okay? So we're looking for time, aren't we? Now we have to take and find distance and speed. Well, the first thing is distance. When we observe our plot, we see that we knew he was here at 1400, and we know he's here at 1406. I'm trying to find out when he's going to get down here, aren't I? That's the question. Well, essentially, it's no different than an ETA problem. You guys do these all the time, okay? We need to measure the distance, okay, from here to here. And you do that with your compass. Do it now. Just take your compass and measure from M to that point of CPA. So we have 8.9 nautical miles, okay? Now we have the distance, but now we need the speed. Now, what's the only speed you really know right now? We only know our true speed, don't we? Okay? We have to establish what the speed of the vessel is down this relative motion line. The only place that's available is what we know right here, okay? And so in order to calculate speed, it's distance divided by time. So what I want you to do is measure the distance from R to M. It was 2.5 nautical miles in 6 minutes. So we have to take the time. Now, can we put 6 minutes in our formula here?
No.
Nope. We have to put it in tenths of an hour. So if we take 6 minutes and divide it by 60, what are we going to get?
0.1.
0.1. So we're going to divide 2.5 by 0.1, and this is where the 10th rule comes into effect. We're going to move the decimal point over 1. So the relative motion speed of the target is 25 knots. And I labeled it wrong. We'll correct that. Okay, so 25 knots. So here is our speed that we use in this problem, okay, is 25 knots. That's his relative motion speed. We call this the RMS. Okay? And that's an algebraic summation of his course and speed and my course and speed down the relative motion line. 0.35.
Now I've got to multiply that by 60, correct?
Okay. All right, we have 0.35. Now that's in tenths of an hour, isn't it? That doesn't do us any good. So we got to multiply this times 60 in order to transfer it into minutes. And what do we get?
0.3.
21.3?
Yeah.
Okay. So 21.3. Now when you get this number, you can round it off. So we're going to use 21 minutes.
Okay.
All right. Now, if you look up here for a minute, that's the time it takes him to go from M to CPA was 21 minutes. All right. But the answers that we're looking for all the time are the reality on my bridge clock or my wristwatch, whatever the ship's time is. And what is the time on our ship? It's 1406 was the last known time. And since we established the distance run from M to CPA, we have to use the time from M, 1406, and we're going to add this 21 minutes to establish the actual time of CPA. And of course we get 1427. So that is the time of CPA. Okay, 1427. So this takes us from step 1 to step 5 in our quick reference guide sheet. Okay, and we've established the threat of this particular target. We know when the CPA time would occur. We have about 21 minutes to make a decision. Okay, we hopefully want to make that course change, if we have to, way before 21 minutes, okay, goes by. So it just shows us that we don't have much time here. We've got to act, all right?
Because he's traveling at 25 knots, so he's moving.
His relative motion speed is 25 knots. Now that is not his true speed. That's our next step. In step 2, we're going to establish the target ship's actual course and speed. Okay? This speed is his relative motion speed as he travels down this line. Okay? So that is step 1. We've established the CPA distance, bearing, and time. Okay? We've labeled our target. We did R as the first plot. M was the second plot at 1406. We established the CPA point. Once we establish the CPA point, which is always 90 degrees to the relative motion line, we were then able to find out the distance and the bearing and the time. All right, so let's go ahead and practice these on paper now, and we'll do a few of these until it becomes second nature to us.